Hey everyone, welcome. So my name is Henri Lieutaud. I work at the Starknet Foundation. I'm the head of developer relations. And today I'm going to talk to you about proving. It was apparently a requested topic from a large number of people. What is Stwo exactly? Stwo is the new prover that was announced recently to be being developed. So I'm going to try to explain to you in simple terms what it is, how it was designed, and what will be its impact on Starknet. So it's Stwo for dummies. I hope there are dummies in the audience. There for sure is a dummy on stage, so please bear with me. These are complex topics. I'll try to explain it in a clear way. So here's the agenda I'm going to follow. We're going to start by a small overview of what proving is, what exactly proving means. I'm going to talk a little bit then about how this is used in production. How do we use proving for Starknet? Then I'm going to talk about Stwo and Circle Starks, which are the new announcements that were made. And finally, I'm going to talk about what are the consequences we expect that Circle Stark and Stwo will bring in production. So a small LI5 on proving. Starknet uses validity proofs. Validity proofs are a cryptographic primitive that allow a person to run a computation, to run a computer program, and to generate a proof that he ran that computation correctly. When he sends that proof to another person, that person can verify that proof and be convinced that the program was run correctly and that the output is correct without having to run themselves the program. Okay? So it allows one person to run a program to do the right thing and convince another person that he did the right thing without this person having to re-execute it. And where proofs really get magic is here. It's in the asymmetry there is between proving and verification. Proving and verification. Verifying a proof is much cheaper than generating a proof or executing the program. So you make it possible for a person with a small device to check the work that somebody has done with a very large device or with a supercomputer. That's how we scale blockchains. It allows networks like Starknet to be operated on very big machines that process a lot of transactions, and it allows the execution of this blockchain to be controlled by much smaller devices like laptops and ideally in the future, cell phones. So how does proving work, right? What is exactly proving? What do we mean by proving? So without going too much into details, proving essentially means representing a computational problem under the form of a polynomial. So if you've done some maths at school, polynomials are, x squared plus ax squared plus bx to the power of 3 and so on, right? But very complex and very heavy one. When you're running a computation in order to prove it, your computer program is represented as a set of values in columns, and each of those columns has a mathematical relationship with the one neighboring it. Every state of your execution, every time a counter in your execution changes, is added up, and you end up with something that is called the execution trace. The execution trace is a set of numbers, and all of those numbers, if they follow the computation you're trying to prove, will be points on the polynomial that has been defined, right? Now, so I hope this makes sense so far. Now, one other element I want to add here is that this polynomial, you're not using it in an infinite set of numbers. In order for your computation to be provable efficiently, you will evaluate this polynomial on a restricted domain, what we call the finite field, okay? In other words, your polynomial is evaluated modulo p, okay? Where p is a prime number that defines the size of your field. Okay? Now, you've evaluated, you've run your program, you've generated a set of numbers. Proving is really the act of the prover convincing the verifier that all of those points fall into the polynomial without having to disclose all of those points, or without having the verifier having to verify all of those points. This is where the asymmetry comes from, right? The prover has to execute everything at its stage. The verifier doesn't. It just has a part of the information. In order to be able to do that, the Stark protocol uses two very important algorithms: fast Fourier transform, which were invented by Fourier, and fast Reed-Solomon interactive oracle proofs of proximity, which is a subset of Reed-Solomon error correcting code, which are something that are very used in telecommunication. So here on that image, you have Fourier, Reed, and Solomon having tea because we're in London. Okay, being able to use FFT and Fry in order to to evaluate those polynomials very largely depends on the value of P. Okay, so that's what I want you to remember, is that the size of your field will impact whether you can use FFT or Fry. And I'll come back to it later. So that's proving in a nutshell. Now, how do we use it in production? Currently, where is this used? So the basic unit you have is Cairo, which you may have heard of. So Cairo is a very confusing name because it designates a lot of different stuff, but the very first thing it designates is the Cairo CPU. It's the CPU air, right? So, when I say that proving involves taking a computation and putting it over a polynomial, depending on the computation you want to execute, you will have different polynomials. Cairo is essentially a set of instructions that define a CPU, like the one you have in your computer or on your cell phone, but this one is virtual, okay? So it defines a set of instructions, and when you use those set of instructions, you can write any kind of computation. So the Cairo CPU, it really is this. It's a virtual piece of, it's a virtual CPU over which you can write arbitrary programs. And the specific set of instructions of this CPU is provable. You can generate proofs for it. And that's the magic with Cairo. The really cool thing about Cairo is that the way the CPU is designed means that you can plug different proving algorithm below it. So you can actually prove Cairo with various proving systems. It's not depending on a single prover and a single algorithm. So that's Cairo. On top of Cairo, now you have Stone, or ST1, right? So Stone is the prover, the actual polynomial that is used to prove Cairo today in production. It has a relatively large prime field size of the order of 2 to the power of 251. It works well. You can prove stuff with it. It has been used for years in production today, for Starknet, for StarkX. It works well, but the size of P, 2 to the power of 251, is relatively large. It's easy for computers to deal with it, but it's a relatively big number. Numbers can be pretty big, and so there is an overhead when computers need to prove stuff with this kind of field. Now, the third point here is sharp. So sharp, which you may have heard of, is I would say it's a batching mechanism for Stone proofs. It's essentially a backend tool that is run by Starkware that allows to take various Cairo programs and aggregate them and generate a single proof for them, right? So you can use, so Sharp also, it is dependent on Stone, but it could be used with another prover, right? So of those three steps, there's Cairo, Stone, and Sharp. Here we're really talking about the prover. So we're talking about the middle, the one that is in the middle. Okay, so now let's talk really about Stwo and Circle Starks. So you remember that I mentioned that in order to be able to use FFT and Fry in the Stark protocol, you need P to have specific characteristic. The specific characteristic we were looking at in the beginning, when Stone was designed, was that when you take P, a prime number, P minus 1 has to be divisible by a large power of 2. If you don't have that property, you can't use FFT and Fry in a proper way, and you can't have the Stark protocol. So there's not that many P's you could choose to get to that property. Okay? So that's how we came up with a field of size 2 to the power 251. Recently, researchers at Starkware, as well as Polygon Labs, released a paper called Circle Stark. Circle Stark is a new protocol that allows uses fancy math techniques so that the P you're able to choose has slightly different property. You can now choose a prime field size such that P plus 1 is now divisible by a large power of 2. So before we had P minus 1, now we have P plus 1. That's all great. What is the impact of this? Well, the impact of this is that some prime fields, some prime numbers that previously weren't usable now become usable. And specifically, the M31 field, M for Marin Mersenne, who is a French monk from the 1600s or something, who studied prime numbers for a long time, and he wrote a lot about those prime numbers. He defined that field, right? And so, if you noticed, M31 is much smaller because it's 2 to the power of 31. It's the order of 2 to the power of 31 rather than 2 to the power of 251. So that gives you now a very nice property, which is that generating a proof can be done over a much smaller field size. So now modern computers, have to deal with smaller number, which actually makes things easier for them, right? You're closer to the optimal word size for a CPU, right? So essentially, Circle Stark allows proving stuff using smaller numbers, right? So what does it mean to have easier proofs, right? It means you can generate proofs faster and you can generate proofs cheaper. Let's get into what that means exactly. So first of all, what is 2? After ST1, you get S2. Bad pun, I know, but it's okay. So Stwo is an open source implementation of Circle Stark for Cairo. It's a prover for the Cairo CPU using the Circle Stark protocol. Eventually, it will replace Stone in production, and this won't change anything on Starknet, on the way you write smart contracts on Starknet, and the way the network is currently used. So it will be largely a back-end change. But what impact will it have? Well, the first thing is you'll get faster proof. This means that generating a proof will be done in a smaller time frame. Today, you may know that there is a delay between when a block is closed on Starknet and when it is actually proven. Having proofs that can be generated 100 times faster, I wasn't supposed to say it, but Oren said it earlier, so now I can. Having proofs that can be generated orders of magnitude faster than today will allow to have lower finality in ZK rollups, and specifically on Starknet. It will allow to have proof that what was done just moments earlier is valid. It will make it a possibility, right? So it will bring us closer to a world in which you have very large sequencers that generate blocks and then generate proofs very closely after, and those proofs can be verified by small devices such as cell phone, Raspberry Pi, fridges, you name it. So that's faster proofs, right? That will be very good and it will make the UX much better. But you also get cheaper proofs. Cheaper as in they're easier to compute. So you can do them on smaller devices. It will bring the cost of running your own L3 or your own L2 down because it will be cheaper for you to actually generate a proof. But also, it will open up the possibility to have client-side proving much more granular. It will open up the door to having users generate a lot more proofs than what they do now. If generating a proof today takes you, I don't know, a minute, and it is brought down to seconds, it becomes possible for you to generate proofs to, for example, sign transactions for your wallet. So it will expand what is doable off-chain by users, and it will bring a lot of usability and a lot of new features in wallets, for example. That's probably just the tip of the iceberg. It will bring a lot of features for what users can do with their own devices. All right, so to sum up, reaching the end of my presentation, Stwo is cool. It's an open source prover for Cairo using groundbreaking novel Circle Stark. It will make proving much faster, much cheaper. It will be invisible for users and devs on Starknet. And it will enable a network that is more resilient, easier to audit for users with small devices, and it will open up a whole range of possibilities to bring off-chain computation by users on-chain. And that's the end of my presentation. I hope this was useful. And if there's any question, I'm happy to take them. Let's make first a quick show of hands. Who thought this was too difficult? Who thought this was too easy? Nice, right? Who learned something? Perfect, thank you. Thank you.